Okay, so what I'm going to do is I'm going to try to add to that. I'm going to take a deeper dive, especially into the science, into the lighting, and sort of bring this home to Monterey, in this area. We have the benefit of having a darker sky here. I'll show you some light pollution maps, but a lot of times I give these talks, it's about reclaiming the dark. In an area like this, it's more about preserving it, maybe making it a bit darker if we can, but we've got the dark skies. It's pretty decent. It's not perfect, but we can always do better. So I'm Destin Hellman. I am a professor of chemistry and biochemistry at Worcester Polytechnic Institute. My expertise is actually in cancer biology. It's in cancer biochemistry. I study cancer cells, how cancer forms, and I study viruses that can kill cancer, and that's fun. So astronomy is kind of like it's a fun thing for me. It's a hobby. But a lot of the chemistry that we do, a lot of the ways that we study cells and study molecules has to do with how they interact with light. So there's a lot of science around how cells, how our bodies, how our brains interact with light, and that's sort of where I got bridged into the science of this. I'm a member of the International Dark Sky Association, Massachusetts chapter. So here we go. There's this thing called the Bortle scale, and it's a way to judge how dark your sky is. The higher the number, the worse it is. So if you're from New York City, you won't even get those stars, right? So it's a Bortle above number, right? So suburban areas and transition areas, Bortle 7, Bortle 5. I have, my house is in Southborough, so that's right near Framingham, but we've got probably a Bortle 5 or so there, if it's clear, maybe Bortle 6. So it's not so bad. Here, we've probably got a Bortle 3 at least. Probably not Bortle 1. So the darker it gets, the more stars you can see, is what this is all about. It only takes a few lights, just a few, to take you from a Bortle 1 to a Bortle 3. One backyard light that's shining there can do that for you. So it's got to be really dark. Yeah.
Is this like an average over a year? Or
no, this is just you walk outside, and this is how dark your skies are because of all the light pollution. So if you've got gobs of light pollution in the inner city, you can't see hardly any stars at all. And the less light pollution you have, the darker your sky gets, then the lower you go.
So it's like a day-to-day kind of...
Yeah, and this can, like they were saying in the video, this can change like that. If everybody in New York City turned off their lights, then you have a Bortle 3. Right? New Jersey would still be over there. So this is something that we can deal with. Anybody remember the Great Northeast Blackout of 2003? Right? You think this? I was trying to actually remember. It was a while because I didn't have the slide in my talk for a while. I'm like, was that an ice storm or something? No, it was a computer glitch. Right? Welcome to the future. Knocked out most of the power in the northeastern United States and parts of Canada. At that time, Todd Carlson was an editor of Sky News magazine, and took what I'm calling an after and before. This was the before. It's actually something he took after. This is over his house, regular city lights, and this is during the Northeast blackout. That's the difference. Lights go out, and we get the Milky Way back. So this is a picture that one of my students took from Namibia. She went on a global project for her degree to Namibia to work on water reclamation, things like that. And I told her, bring your camera, point it up, take a bunch of pictures, and I'll figure out how to process it later. Yeah. And this was some of the pictures that she took. And this is a super dark area where the Milky Way is obvious. In fact, you can even walk by the light of it. The starlight itself is enough. Your eyes can adjust to it. It's amazing what our eyes can adjust to. So this is what light pollution looked like, well, more than 10 years ago. But I'm going to show you a 10-year gap. I think this is something like 2006 to 2016, something like that. But, so it's a little bit subtle, but this is a 10-year change. I want you to look at the area around the Great Lakes. I'll do this a bunch so you can see it. But this is only 10 years. The change in light pollution. There's the difference. It's easiest to see when I go back. And you can look in some of the areas on the eastern seaboard. But this is actually quite a difference. If you live in these areas that are, in southern Michigan, you're seeing a massive difference in this, and especially in these areas around Boston and stuff like that. So if I really bring this home, this is Massachusetts. Okay, right? Boston, Worcester, of course. Springfield, yeah. But this is Monterey, right here. We have this sort of dark band right through the Berkshires. This is something that we can claim. Pittsfield is encroaching in on it. Northampton, Amherst, and Springfield are encroaching in on this. That little dot right there is Beckett. They're all in the process right now of turning over to LEDs and streetlights in so many of these communities. But I wanted to show this because we do have access to these dark skies. Certain light pollution maps will give you dark blue to show you a Bortle 2 or 3. This one doesn't do that, but this is actually a dark blue zone. It's not black. If you go up here into the northern areas of the Berkshires, that's where we get very, very dark. So it's all about keeping that. This is a picture of the International Space Station of Milan in 2012 and 2016. This is before and after they converted to LEDs. Stark difference. This was the first generation of LED streetlights that were put up. They were very bright, very blue, and you can see the difference from here. The amount of glare is tremendous with these. I was just in Baltimore for a conference about a month ago, and Baltimore is probably the worst city in the United States in terms of LED streetlights because they converted right away with the new technology before we had warm LEDs, and it's super bright. So this is what we want to avoid. We don't want to end up like this. Any Pink Floyd fans out there? So we can take white light, we can put it through a prism, and it splits into its colors. Right? Sunlight will do this, and white light that we produce will do this. So all of these different color wavelengths are in that white light to different proportions. And that's how we get sort of cool light or warm light, because the colors are in different proportions in these. This would be an example of a high-pressure sodium lamp, which is consistent with the street lights that we have outside, which would be one of those across the way. They're very, very amber, very yellow, very warm lights. Those are high-pressure sodium. Those are very different from the LED lights that we have now. So if we split the spectrum, if we put that light through a prism and we split it out, this is what the high-pressure sodium looks like. It's actually a little blown out, but it looks very different from the LEDs. This is called an emission light. The light is produced from the bulb, but only in very specific areas of the spectrum. It only produces a lot of certain colors and little of others. And it's difficult to see here. I'll show you if we explode this up into a graph. To actually look at how much of each of those colors is there, then we can really tell what's going on. So with the high pressure sodium, this is the reason why they're orange and amber, because that's most of the light they have. And you see down here in the high energy blue area, there's very little. This is the technology we've had for decades and decades and decades and decades. It turns out we were lucky. We developed the technology because these bulbs last forever, not really having much science dedicated to what color is healthy. Nobody had their eye on that. So we were lucky. We've had these lights for a very long time, and they have relatively minimal impact to the environment, except for the fact that they make things brighter. Now, with the advent of these LEDs, you have what we call the Blue Mountain. So not only is this what we call broad spectrum, you see it's producing all colors. It's pretty much like the sun. It produces all the different colors in varying amounts, except it has this blue mountain, and this is the highest energy light that's there. This is the bad stuff. This is what we want to avoid. And so part of what's most surprising when I give this talk to a lot of folks is light can be harmful. We know things about UV light and putting sunscreen on and stuff like that, but blue light can be harmful depending on what time of day, or night rather, you're exposed to it. So I'm going to talk a little bit about the science behind that. These are different color temperatures. So just like they said in the video, you can look on the back of the bulb, or you can talk to Eversource or National Grid when they're putting the streetlights in for what we call the correlated color temperature. It's basically just the color of the bulb, but there's a number associated with it in a unit called kelvins. It actually comes from back when Harvard College Observatory was learning about stars, and all of the amazing team of women was calculating all of the spectral lines for the stars and figuring out what the stars were made of. It was an incredible place. This is where it comes from. But like I said in the video, the lower the number, the better. And you can see that it doesn't necessarily change this part of the bulb. We do get different amounts of that relative to the blue. So if you're at 5,000 K, this is very blue, and that's because you have comparatively more blue than you have in this stuff. 4,000 has less, 3,000 even less, but look, you've still got a blue mountain with 3,000. So this is going to be a warmer bulb. If you've still got a blue mountain there, not until you start getting down to the 2700 or 2200 Kelvin range do you really start to get rid of that. This bulb that we're looking at outside the window there is at least as low as a 2200, if not lower. So those really deep ambers are what we want. It's sort of what we're used to. But the higher we go, the more of that blue mountain we put into it. So why do we care? Why blue matters? There's a lot of organisms on this planet that have grown for a long time. And although the sky wasn't always blue in the daytime, it has been for a few billion years, we have evolved under a blue daylight sky. Blue is the most abundant visible color in our atmosphere. The blue light has the highest energy. It hits the molecules in our atmosphere, mostly nitrogen, and gets scattered everywhere. And that's what we have in the daytime. So it's no surprise that everything from plants to insects to fox to turtles and humans have evolved to respond to the daylight, to respond to the blue light. Either if you're nocturnal, to go to sleep, or if you're diurnal, like us, it's to be awake in there. And it changes our body chemistry when we're exposed to blue light. We have what's called a circadian rhythm. Most of you probably have heard of a circadian rhythm before, circadian clock, yeah. This is actually a biochemical pathway. There are proteins in your body that respond to light. What happens in your body, in part, is that when this blue light is there in the daytime, it signals a waking state for us. It changes the chemistry in our brains, and changes the hormones in our body, changes the way our organs process things, our digestion, our immunity, our brains. They all change chemistry to be awake and alert and doing different things. You actually digest food differently when you're sleeping than you do when you're awake. Your immune system does different things when you're sleeping than when you're awake. So there's a lot of things that are hormonally controlled. In the evening, this goes down, and this is the dark of the sky. Big surprise, nighttime is actually supposed to be dark, right? So when we're leaving lights on outside, if there's a parking lot like this, even small amounts of light that are encroaching through a window changes that chemistry. The brighter it is and the bluer it is, the more it changes that chemistry. It's to the point where if we are introducing blue light down here, we start to change that chemistry. This normally signals a waking state, high alertness, and more coordination. And what this is doing is it's changing fundamentally our melatonin levels. How many of you have heard of melatonin, right? It's one of those things you can buy at CVS and take it, right? And there's questionable pharmacology about this stuff, but you take it and it makes you sleepy and that kind of thing. You have normal melatonin levels. The melatonin levels respond to the absence of light and the absence of blue, signaling that it's a dark time, it's time for us to get sleepy, it's time for our body to start to adjust and to do the things we're supposed to be sleeping. So if you have even small amounts of light or blue light at night, it disrupts our sleep cycles, and it can lead to, over a period of time, mood disorders. Because melatonin is plugged into the way that we digest things, it can enhance your chances of getting type 2 diabetes. And as they mentioned in the video, and this is newer data, but it's pretty rock solid, is that because many cancers are hormonal, we call them, they respond to hormones, and they grow because of the presence of them, melatonin plugs into that stuff. So we find that the hormonal cancers, like breast cancer, prostate cancer, are significantly higher in folks who are exposed to a lot of light at night. And it's constantly disrupting their cycles. So studies are looking at doctors and nurses that work midnight shifts, and then they don't get enough sleep or sleep in dark times to do that. And they have much higher incidences of these types of cancers. So it's really weird to be talking. I'm a biochemist, and I find it weird that exposure to blue light at night can raise your incidences of these things. Yeah.
One question. Does it need to come in through your eyes at
yes.
night? Or...
We'll talk about that. Yes,
okay.
It actually does. Yeah. That's a great question. Yeah.
Is a computer screen blue light?
Yeah. We're going to talk about that too. I got you covered. So in 2016, the American Medical Association adopted guidance. The science was strong enough that the AMA decided to put out a white paper and issue a declaration that says we have to watch the LEDs. We have to be careful with these because the science is pretty solid on this stuff. And adopted language for this saying we have to be careful of LEDs, we have to be careful of the glare and the bright lights, but also the blue light because of medical issues that we can develop. Started to put this on the radar. At the same time, they started, Mari Emoto was one of the physicians, cardiologists that was on the board at the time that helped to do this. And along with a team from Massachusetts, IDA has been trying for years to push a dueling bills in the House and Senate for the State House, State Senate for Massachusetts to adopt dark sky legislation. It's gotten closer and closer each and every year. It's up again, so call your Congress folks and let them know to support it. Many of you that have, probably the bulk of us have iPhones or something like that, or Android phones, but they all have night shift functions on them. Are you aware of this? Have you noticed that when you're using your cell phone about 10 p.m. by default, if you don't change it, all of a sudden your screen colors get weird and change? It's because it takes the blue out of your screen. Because that blue light entering through your eyes disrupts your sleep cycles. So when the sun has waned and you're starting to get sleepy, if you're exposing yourself to that blue light, you're suppressing that melatonin that's supposed to be there. It can have pretty dramatic effects, especially on young people. So it's already in our tech. It's already there. We just have to be a little more aware of it. Here is an article that came out. This was only a couple of weeks ago. So this is a QR code. If you want to, you can grab your cell phones and scan this so that you have it. But this is a Washington Post article. I think it's excellent. It covers everything I'm covering in this talk. And it's just wonderfully written. So I wanted to do that. But while I do that, and you pull your phones out and scan that, I'm going to throw a big science term at you. I promise I'm not going to do this too much. There's something in your brain, a part of your brain, called the suprachiasmatic nucleus. It is connected to your eyeballs and your optic nerve. It detects light and is particularly sensitive to blue light, but it has nothing to do with vision. That suprachiasmatic nucleus is responsible for sensing the blue light in daytime and signaling through your brain to the melatonin pathway, whether or not you're supposed to be awake. So that's how we're plugged into it. So the answer to that excellent question is yes. It actually depends on whether it's coming through our eyes. So because our eyelids are not completely dark shaded, I don't know about yours, but I don't paint my eyelids before I go to sleep or something like that, light does penetrate that thin eyelid that you have. And so even if your eyes are closed, light can still get through. We know that, right? If it's a bright day outside, you close your eyes, you look up at the sky, you can see red because you're looking at the blood vessels in your own eyeball. So light can get through. But certainly, if your eyes are open, it's not just us. We're not the only ones with that part of our brain that responds to it, responds to that blue light. And this is me trying to pander and put a bunch of cute animals on here to get everybody. No, these are actually native species we have in Massachusetts: loggerheads and red fox and spring peepers and fireflies. We don't see many of those anymore. I remember growing up when I was a kid, tons, gobs of fireflies everywhere. It was a relatively rural area, but not too much. Gobs of fireflies, not so much anymore. They're particularly sensitive to light pollution. In particular, let me just very quickly highlight some of these. Many of these species are nocturnal. So obviously light pollution dramatically affects them. We know that when loggerheads are born and they're supposed to be crawling out by the moonlight into the ocean, they're going the opposite way. There's a lot of scientists that are herding these things into the ocean because they're literally crawling the wrong way. They talked in the video about birds. Many migratory species, even down to monarch butterflies, are dramatically affected by light pollution. They literally go the wrong way. Things like fish species. This is something that I learned only recently, but fisheries that produce fish for our food actually use bright lights to prevent the fish from starting their reproductive cycle because they like it to be dark and they go through a cyclic pattern. Fish like to hide. They like to be in dark places. That makes them feel safe. That's why when we go fishing, you always fish around the dock because they're hiding under there. When we expose them to more light, they tend to reproduce less. It actually affects their growth as well. We find that there are lots of studies that show that if you put too much light on fish, they don't grow as large. So it has pretty dramatic effects. They talked about moths in the video. And so there's different ways that different species are impacted by this, including us. So we have the fortunate position of having all this stuff, plus mood disorders and all kinds of other different things. This is one of the big ticket items. We've had artificial light for hundreds of years. We've grown up under the lights for thousands and thousands and thousands of years. And for some strange reason, we're still afraid of the dark. We're still afraid of the dark. We still feel less safe for evolutionary reasons in the dark. One of the things that we try to decouple as many of us talk about light pollution and safety is to decouple this idea that brighter is safer. It's not. There's not a single scientific study, I've looked hard, all of us have, not a single scientific study that shows if you brighten a place, crime goes down. There's no correlation to it whatsoever. In fact, probably the strongest study was in Australia they did a number of years ago that showed if they increased the lights, crime went up. And it was probably because of increased glare. But there's no hardened evidence for that. Crime, surprise, takes place in the daytime too. So that really is a regional thing rather than how bright things are. It's also, we want to dig deep and realize that our eyes have an incredible ability to adjust. And that the worst thing, as they said in the video, is for us to put lights in places where there's glare. Glare, I'm going to define it a different way than did in the video, a really easy way. If you can see the bulb, then you have glare. That's the easy way to define it. It's light that's traveling from the luminaire, from the bulb, directly into your eyes. And that's not useful at all. In fact, it's detrimental. You can't see anything else if you're blinded by those lights. We want light illuminating the stuff that we're interested in, right? The ground and the backyard and the dog and stuff like that. Only for a little bit of time. Then we go to sleep, turn the lights out. But if that light is shining directly at our eyes, it's not helping at all. Here's an example. Here's a nice college campus, I don't know where this is, where they just blasted the whole campus with blue lights. All the college students are having mood disorders and stuff like that. Now you see the college student there, now you don't. They're actually still there. Can you find them? Amazingly enough, he's actually standing right underneath the lamp. He's right there, standing under the lamp. And the reason is because just like your eyeballs, the camera cannot detect enough in the dark areas because of the glare. Because the bulb is shining directly into the camera lens. Same thing happens with your eyeballs. Here's another hand, because the light shines sort of sideways and up. And as they said in the video, that's wasted money. It's amazing if you look all around at all the lights. Any light that's shining laterally out, which is glare, or up into the sky, is literally wasted money. It's grinding away using electricity off the grid, and it's not doing anything. In fact, it's a hindrance. Same thing. If the person puts their hand up and blocks the light from coming into the camera, does the same thing your eyeballs would, now you can see there's somebody standing in the fence. This is what glare does. It's so important. And blue light, being higher energy, has much more glare. And the reason why is because higher energy light can scatter more. It's one of the reasons the sky is so blue, because blue light is the highest energy. It scatters the most. So the bluer the light we get, the more glare you're going to have, but also the brighter light. So it's about shielding. It's about pointing the light where we need it. It's about taking the blue out of it so we don't have all the biochemical problems. And avoiding this stuff. So there's just responsible ways to do this. Here's one example. Mammoth Cave National Park in Kentucky just became an international dark sky site. They have a certification now, and this is what it looked like before and after. This is simply the difference between lights where we're not paying any attention to what we put up, and lights that we pay attention to the stuff. They're warm, they're shielded, and look how much more pleasant that looks, right? It's illuminating the stuff. And the reason why we can't see the fine features of the brick and the slats on the shutters and that kind of stuff is because of glare. It's completely because of glare for that. So there's easy solutions, right? Don't buy these ones. Don't put them up in town. They're bad. They're bright. We don't like them. They have more glare. They scatter off stuff. So let's say that your neighbor really likes one of these things, and they put up a really bright 6,000 Kelvin light that they're shining into their yard, and it's shielded and everything, but they have one of those really bright white fences that's in the back of their yard. That light shines on the fence, and because it's got so much blue in it, in particular, it scatters off of that fence and just reflects back out into the trees and in your yard. So it's not just about where we put the light, it's about the color temperature. It's about the wattage and all that. But we want to aim for something, and I would say at least 2,700 Kelvin, if not less, 2,200 Kelvin for these. Yeah.
Did you ever speak to this, my ignorance? What's the problem with the sodium?
Well, nothing, right? They gobble a lot of electricity relative to the lights we have now. Yeah. So to give you an example that's inside your house, a typical 100-watt incandescent light bulb that we've used for decades and everything consumes 100 watts, right? Where you replace that with an LED, and the LED uses 5 watts. So it's that big of a difference.
So that's comparable to these?
Yeah, so the high-pressure sodium, they're using a lot of electricity. So we can do this where we save the towns, we save ourselves lots of electricity, right? And that goes well beyond the electricity we consume. It goes to carbon content in the atmosphere and all that stuff, because of how we're making the electricity. But if we're not careful, we'll put the wrong kind of light in there. And then we're going to introduce a whole different problem. So we'll start saving the money and saving the planet and all that stuff, and we're going to start harming everything even more by putting this light in there. So directing light where it's needed, right? I mean, how many of you have seen globe lights like this in parking lots and places, and you think, oh, they're these acorn lights. They look so pretty, right? They look like the 1800s and stuff like that. They're horrible, right? Everything, if I draw a line, right, everything aside from this, right, all of that light is wasted money and it's light pollution and all that stuff. Bad, better, best. So we want what's called full cutoff. And what that simply means, my definition of this, is you can't see the bulb. If you can't see the bulb, there's no glare, and if you can't see the bulb, it means it's shining downward on something that it's supposed to be illuminating. One thing that I take issue with, that they said in the video, there's one person that said that right now corporations and businesses are not affecting the night sky. They're not affecting the sky. They don't have things up there. That's not true.
Yeah.
Right? Ever seen the Starlink satellites that are up there? Elon Musk has put 22,000 of these things up there now. I take pictures of space, and I see these things streaking across my photos all the time. So we see that. It's changing the night sky. You can now look up at the night sky, and at any given moment, you will see things that look like stars moving around. So we are changing the night sky in a huge way. And there's going to be in excess of 40,000 of those in the sky. By the end of that, there are 2 other companies that want to put them up. So we may be looking at 60,000 to 70,000 of those satellites.
So, and there's no way to keep them from owning the sky?
Right now, because as per usual, right, the tech moves like this and Congress moves like that. So, right? So we need legislation to catch up with it, and fast. And it's also, you know, the politics of dealing with big business as per usual as well. So it's a tough problem.
And nobody really has jurisdiction.
No, and this is what we have to figure out, right? Who owns space, right? So what can I do to help? Let the night be dark, right? Don't be afraid, it's going to be fine. A lot of people out here, they put the lights out because they don't want the bears or coyotes coming near their house, and that really doesn't do anything. They're going to come anyway. Limit exposure to blue LED at night. Replace your LEDs with less than 3000 K. The warmer, the better. Spread the word and talk to your towns about supporting lighting bylaws. I'm working with a group in Beckett right now. We're sponsoring a lighting bylaw that we're trying to get through. I don't know if anything's going on in Monterey, but I also did this in Southborough. So it's about raising awareness. It's about us learning, right? Learning more about what's going on and how we're affecting things. This is a question I always ask, but I gather that based on the fact that you all live in dark sky areas, you look up more than most. It is very much the case that 80% of the population is growing up right now and they may not ever see the Milky Way. They may not see more than 10 stars in the sky because of where they live, because of light pollution. Where do we want to look? So this is my quick spiel on night tourism, astrotourism, right? We live on a big Frisbee. And it's been really interesting. One of my favorite things in astronomy is reading papers about how do we figure out what our own galaxy looks like? How do you figure out what the outside of your house looks like when you're inside of it? Right? You can send out drones and stuff, but the galaxy is really big. You can't exactly do that. It's really neat how they're doing that. They're gauging distances to each and every star, and they're building a 3D picture of where the stars are to look at what our galaxy looks like. Very cool. We know it's a spiral, it's beautiful, it's got a bar in the middle, but you are here. We're not in the middle. Right, we don't want to be there. There's a supermassive black hole there. We don't want to be there. We are kind of out quite far. It's something called the Orion Spur. But when you look up at the sky, there's basically 2 regions of the sky that you can look at because we live in a Frisbee. You can look up and out or down and out of that Frisbee. You can look at the areas that's not in the plane of the Frisbee, and that's where you're going to see deep, deep, deep space. If you look into the plane of the Frisbee, that's where you're looking at our own galaxy, the Milky Way. So those are the 2 things you can look at. And in the summertime, it's great because right now, and hopefully it's clear outside, maybe we can get a view of something around here, but the Milky Way is directly overhead. Arches high in summer. But if you look down toward this horizon or that, you're looking deeper into space. And so that's what we want to look at. We live on a Frisbee. Here's that picture from Namibia again, and there's the Frisbee. The weirdest thing is this is our view of the Frisbee from within. So if you actually look, if you're able to look through the Earth or look 360 degrees around, you can see Milky Way on that band everywhere because we're inside the Frisbee. But this is what one swath of it looks like from our view in the sky. That bright light that's right here happened to be Saturn. It was up in the sky then, which if you haven't seen through a telescope, you can't look at it now, it's on the other side of the Earth, but it is spectacular. You can see the rings of Saturn. It's absolutely spectacular. It's a jaw-dropping. I like watching people looking at Saturn through a telescope more than I actually like looking at it myself. I've seen footage, right? But I love people looking at it for the first time. So what's out there, right? You grab a telescope. I want one of these. Maybe not that one. The James Webb, right, is an upgrade, but I'll take this one. It's on its last leg. But what's out there? So there have been many different directors for the Hubble telescope, but a number of years ago, one of the directors did something very controversial. They get 4 days of discretionary time because they're the director. They can give it out to folks, right? Here's a Christmas gift or something. Here's some Hubble time. They can direct it towards certain scientific efforts. It's basically a perk that they get. And one of the directors said, I'm going to point the Hubble telescope at the most blank place in the sky. It was actually an area of the Big Dipper, which is out of the plane of the Milky Way. And I want to take as much exposure of one part of the sky as I can for 4 days of exposure. That's a lot. Never having done that before, and this is what we got.
Wow.
This is called the Hubble Deep Field. This is a pretty old picture now, but there's a star, there's a star, and maybe that one right there is a more faint one, and this one. Those two and these two. Everything else you see in here is a galaxy.
Wow.
Everything else. Our galaxy has greater than 500 billion stars in it. And because of photos like this, we estimate that there's something on the order of 500 or 600 billion galaxies out there, each with that number of stars. Because of the Kepler missions, which were studying exoplanets to try to find planets around other stars, in the last 10 years we answered a very interesting question. Do other stars have planets, and how frequent are they? How ubiquitous are planets around other stars? And the answer to that question was pretty exciting. It was that, on average, every single star has at least one planet, and most of them have more than one. And the really interesting question was, how many of them have rocky planets about the size of the Earth that are not too close or not too far away from their star, that they might have liquid water and grow, organisms like us, and we can say hi? More than we thought, many more. From one Kepler mission over a number of years, 4 years, 5 years, we found over 300 of them in one region of the sky. So that's exciting for me, because one of my pet projects in biochem is to study the formation of life and how we only have one example of it here. All the organisms on this planet are derived from the same progenitor. So we're all built the same. And I want to, as much as I love the biochem on this planet, I'd really like to study somebody else's planet. So then we have the James Webb, and James Webb did the same thing, and it did better. It did it better because it pointed at an area of the sky that has this giant galaxy cluster here. The James Webb stars are easier to pick up because it's got more spikes. Call these the Disney stars, right? They put spikes, right? Those are an artifact of the fact that the mirror in the front is held in place by these metal protuberances that come out. But this galaxy cluster does something really neat. James Webb wanted to throw this out there and illustrate it right away. It's called gravitational lensing. There's so much gravity around this area where there's so many galaxies that they warp space. And that's why you get all these smears around. You see it? It acts like a lens. It's called gravitational lensing. And it actually magnifies and amplifies the things that are behind that. So the Hubble and James Webb now know how to study galaxies that are so far away that the telescopes themselves would not be able to resolve them. They wouldn't be able to see them. Except that because there's this natural lens in front of them, now they can construct a computer model of what the lens looks like, and then they can take the smears out of these galaxies and see exactly what they look like. It's amazing science. Really amazing science. So now we can look at galaxies that were present, the first galaxies in the first 300 million years of the universe as Earth. This is what I put together. My wife decided, she looked at me one day, this was many years ago, and she said, how is it that such a science nerd like you doesn't do astronomy? She bought me a telescope. And she regretted that every day. Because I bought lots more telescopes, and I got tired of setting them up. And so in my backyard in Southborough, I built this little imaging observatory, and that's my, and it's all computerized, and I can go on my iPhone and open the roof and do that, and maybe if it's clear enough tonight, I'll do that from here. But I use it for a lot of outreach for my students. We do studies with it. It's really cool. It's a great project. and I like to take pictures of space. This is a picture of the Iris Nebula from Southborough that is what I'll call unprocessed. Things in space are incredibly dim. Very, very, very dim. Would you believe me if I told you that there is a galaxy in our sky that is 6 times as wide as the full moon every night for most of the summer? The reason you can't see it is because it's very, very dim, but it's that big in the sky. If you looked up in the sky, it would look like that. It's like that big. 6 full moons wide. But it's very dim. That's the Andromeda Galaxy. We can see the core of it with our naked eye in a dark place, and it's the furthest thing that you can see with the naked eye. It's 2.5 million light years away. So if you were traveling at 670 million miles an hour, right, down the Mass Pike, right, and you turned whatever that was, right, toward space, and you traveled at 670 million miles per hour, it would take you 2.5 million years at that speed to reach the Andromeda Galaxy. That's the next closest regular galaxy to us. It's kind of far away, but it's that big in the sky. It's even bigger than our Milky Way, and it's gorgeous. I'll show you a picture of it in a minute. This is what the Iris Nebula looks like. This is a dusty reflection nebula without much processing. So most of astrophoto processing, you have to brighten everything. And the trick is to brighten the object and not brighten the stars. You sort of suppress the stars and brighten the object. We have to brighten it a lot more because even with a camera, it doesn't come out so bright. So I didn't brighten this much. But this is from Southborough. This is the picture I took of the same object with the same telescope. I lugged it all the way out here before I built the observatory. This is from Beckett. Without any excess brightening. That's the difference. That's light pollution for me. This is what I deal with, right? That's the difference. And if I brighten this up, I don't even know if I have a slide for that. But, oh yeah, here it is. That's what it looks like if you brighten it. The dust of space, and this little nebula. This is a hot blue giant star that's sitting in the center of this dust cloud. It's just illuminating it with all this blue-violet light, of course. But that's what it looks like when you brighten it. But just right out of the camera, there's a huge difference with the light pollution. One of the features that I have on my cameras, which my wife doesn't like looking at this slide either, well, there's the Andromeda Galaxy, brightened. And it actually has a couple of satellite galaxies that it absorbed. It's in the process of sucking all the stars out of those. And it's all kinds of fun stuff. My wife loves this slide, because then I have a special camera. I used to take pictures with a DSLR just strapped to the telescope, and now I have a special camera. Those are all filters. Those are filters that either block light pollution, because space only has certain wavelengths of light to come through, only certain colors. There's nothing much that's green in space, for example, so you can filter that out. But some of these, they filter to such a degree that they only let the exact wavelength through that hydrogen produces, for example, or oxygen produces, or sulfur in space. The same way the Hubble telescope takes pictures. In fact, because the tech is so old now on the Hubble, this actually has the same chip that the Hubble does too. So this is like a Hubble camera, and you can buy it now because they're relatively cheap. But what's neat about this is it means that I can do science in space. When I'm taking pictures, I can take pictures of just the hydrogen. And that's neat because we can do spatial chemistry with my students. So if we do that, this is an example. This is called the Veil Nebula. It's right above our heads right now. It's in the constellation Cygnus, the swan. It's right out on sort of one of the bird's wings out here. This is the guts of an exploded star that's up there. The red is hydrogen and the blue is oxygen, because that's how they glow. The reason these are glowing is because the gases are hot. They're thousands of degrees. And when you heat those gases up that much, they actually start to glow for colors that are very specific for the elements. So this is one of the ways that you can do chemistry from space. So that's from a supernova explosion. This is another area in Cygnus that I just thought it was pretty because you get a little bit of dust and one really nice star, which I put the Disney spikes on because that's just pandering to people. We like to see, seeing stars like this just makes us happy. This is called the Pelican Nebula. It's also, you see, these are all from Cygnus. From Cygnus, and I took this picture not to make a pretty picture. I take a lot of pictures just to see stuff, to see if I can capture something. And it may be very difficult to see, but does anybody see this pillar here? You see those little white things that are coming out on the tip of it to the left and right? You might not be able to see. That's called a Herbig-Haro body. It turns out that these pillars that are everywhere in different nebulae, they mark where gases are really dense. They don't get blown away by other things in space because the gases are collecting because it's a stellar nursery. There's a newborn star that's going to be there. And right before the star is born, which means thousands of years, but right before the star is born, it starts to spin up, and as it absorbs that gas, it starts to blow these gases out at high energy, and it has polar jets. So those jets, I wanted to see if I could take a picture of those jets. So those little tiny white things are what I was after in this picture. And that means there's about a star that's about to be born. And when it is, it's going to ignite, nuclear fusion is going to start, it'll blow the cocoon away, and then you'll see this gorgeous star that's there.
So how long will it be until people can see the star that's probably already formed?
It could be hundreds of years. It could be tomorrow. It could be thousands. Like one of the things is the star Betelgeuse that's in Orion's left armpit, I think it's, right? Very bright star. In the winter you can see a very orange star. It's a red giant. It is about to go. It's about to go supernova. When that star goes supernova, we will notice that there is a star in the sky at night that's brighter than the sun. So bright that it'll illuminate the sky like a full moon. It'll last about 10 days, and it will start to get dimmer and dimmer and dimmer until it's gone. That'll be spectacular. We may actually get to see it, or it may be in like 400 years, or maybe 1,000 years. So we're just not accurate enough at predicting that stuff. But once they start to do this, we know they're about to be born, but this is time scales for the universe, right? So we may or may not see it, but it would be great if we could. But because this nebula is 2,500 light years away, it means when I took this picture, this is not what the Pelican Nebula looks like now. This is what it looked like 2,500 years ago. Because light takes that long to get here. So it may have already hatched out, but we have to wait until the light reaches us, right? Light is a finite speed for those. And this is, I think this is the last one. This is the Wizard Nebula. This is one of those things where once you see it, you can't see it. But I put it in a different orientation so I couldn't see it. But the wizard's sort of lying on the back with his feet up in the air. Right? Here's the wizard's hat. There's his nose, and his eyeball is that star. And here's his hands right here. Right? So that's the Wizard Nebula. But usually when there are things like that in pictures, I like to turn it so that I don't see it, because once you do, you can't unsee it. But these are very fun things to take pictures of. And that's all of it. So I'll be happy to take any questions you have. I have a telescope set up outside. You probably saw it when you were walking in. It is going to be veritably useless right now because you know, with the brightness we'll have outside, it's not quite dark enough because the sun just hasn't gone down quite enough. There's still going to be some sky glow where the nitrogen is still active in the atmosphere and glows, but there aren't any planets up right now. There's no moon up right now. So the easy targets for the telescope are there. I set it up though because if it happens to be dark enough, we might be able to snag a couple of deep sky targets. But even looking at the stars is okay. But I'm happy to give just a sky tour with our eyeballs, right? It's a great way to view the sky. So for whoever wants to stick around.
So
Yeah.
I'm just going to put out a little plea, like, you know, everyone's like, there's nothing I can do that matters. And I'm like, so as a select person in the town of Monterey, I thank you for coming. And I just want to put a little thank you out to the Pioneer folks that got you to come. But I also want to say to everyone who's here that if you are moved by this and you think that Monterey should try and do our best to not get cold LEDs, do me a favor and go ahead and email the select board, right? Because this is a place where your voices will, I guarantee you, will be heard, right? I'm going to back this because I think the science is pretty strong, and I'm hoping, I know we have a contract with National Grid. I have to look into exactly what the specifics of that are to see if we can bow out until the warmer lights are available. So I'm going to do what I can, but the more of you that write a little note or collect a bunch of signatures or whatever, that gives me a little more power to go in there and say, hey, there's a bunch of people that are behind this. This is not just me being a wacko and saying that we need warmer lights because I hate those blue lights.
Right now, there's no effort to designate this area as dark sky.
I don't think that we put yeah, sure, yes, let's be blue dark skies, but there's not a lot we can do as a town government to require it. But we can choose what goes into our streetlights.
Right,
And
no,
personally, I also want to look into, do we actually need as many streetlights as we have? Because I have the vague feeling that maybe we don't.
Yep.
Right?
Turn them off
You
and
don't
see
have
if
any
anybody
big
even
shopping
notices.
malls and big parks.
Turn them off and see if anybody even notices. That's typically what they do.
But just like, please feel free, like, this is a place where your voices will matter, and it will be helpful to me to be able to say, look, 30 people were there that night, this isn't just me.
And as someone who worked on, we passed the bylaw in Southborough, as someone who's working on one in Beckett right now, it is absolutely refreshing to see a select board member at one of these talks. There's such a good situation here. It's ripe for taking the right steps and doing this without having to get eyeballs deep in town
And we have
politics.
2 of the 3 actually.
Yes,
It's
excellent.
on the
You're not
top.
supposed to say that.
Yeah. Other questions? Yeah.
So the LED lights, so even for bulbs, like in our house with
Yeah.
this thing where, oh, we're not gonna have any more incandescent bulbs, but I think that they must be pretty blue because of the light being lit.
Yes.
So how do I know when I'm ordering online and it says LED bulbs, like, is it just that number you're looking at?
It is. You just look for the
It
number.
really is?
Every single one will have one. It will tell you the CCT, the correlated color temperature, but just look for that 4-digit number with a K at the end of it, and that will tell you. And the lower the number, the better.
That's it?
Yep, that's
It
it.
seems pretty easy.
It is. It's really easy, right? And,
Okay.
and a lot of times we just, you go to Lowe's, you grab a light bulb off the shelf, and you're like, well, it's an LED bulb. I take it home, you put it in, you're like, right? It's a super bright. Like, what is that, right?
That's awesome.
It has to do with the wattage and the correlated color temperature. So go for something that's low wattage. 5 watts is a lot for LED, which is great because we usually had a 100-watt bulb in there, and now we're saving electricity. But go with the warmest color you can. I have yet to encounter a single person that says, no, I prefer the really bright blue ones in my house, right? Because you look at it and you can just feel it's doing something in your brain chemistry, right? Yeah.
What's the Kelvin temperature of the warm incandescent bulb?
That one that's out the window, which you can probably see, is 2200 Kelvin. Something right around there. So that's very amber.
An LED you're assuming.
That's a high pressure sodium, and it doesn't matter what the tech is. The color temperature of the bulb is universal. So that's a color that's 2200 Kelvin or even maybe less.
I'm saying the one that we call
Yeah.
indoor LED.
Indoor?
Indoor.
Yeah. If you want a nice
Incandescent
warm
we
light
used
like
to
these,
have at home.
yeah, this is a great example. These are probably not LEDs, but it's a good example of just a warm light that's not too bright. The brightness is great. This is probably a 2700K bulb, maybe 3000. I'd be surprised though. 3000 tends to be a little bit more blue than that, but that's kind of what you're at. So if you went for a 5-watt bulb, they have dimming LEDs now, which is even better, and as warm as possible. It makes you feel cozy.
So, during your presentation and during the video, they mentioned that it saves money to not have, this much light pollution. But I was wondering because LEDs are only 5 watts versus other lights have been like 100 watts in the past. So wouldn't that be saving more money, or how does that work?
Well, it is, right? So anytime you convert anything to LED, you're saving money, right? The trouble is that with the LEDs, because if you just grab a generic one, they tend to be bluer and brighter with a lot less wattage. So even the 5-watt bulb can be a lot brighter than the one you had before and a lot bluer. And that's sort of, remember that slide I had with Milan that showed before and after they converted? The whole city just looked brighter and not as warm, right? From the International Space Station because of that. So it's one of these things where we have the ability to save gobs of money. To take something that was, if what we're paying right now is 100% of the cost, we can take it at least down to 20% just by doing this, or more. But we can do it safely. We just have to pick the right bulbs. And to the point that your select board member, sorry, I don't remember your name.
It's okay. You don't need to. They're the ones.
To the point that you made about whether National Grid or Eversource has these available, I learned 2 things in working with both of them in different towns. One was that usually if you just call them up and talk to their rep, they will simply say, well, yeah, we've got those. We just have to dig them up. We just have to go get them. Right now, everything all the way through 2700, and for a lot of companies 2200, are the same price. There's no price difference for the correlated color. 0. They're all the same price. And they all have the same wattage benefits and everything. Where you start getting to increase cost with the streetlights is whether they have controllers on them, so you can turn down the wattage if you want, whether they're dimmable at night. Pepperell just put lights in and they dim them to 50% capacity at night. starting at like 2 in the morning or something like that. You can also buy ones that have CCT control, that you can even tune them down to be more yellow or more blue, whatever people like. So there's crazy stuff. Those are expensive, but you don't pay for the color. The problem is that when the first generation of the LED streetlights came out, they were harsh and blue, and everybody stocked up on them, and because everybody went, whoa, we don't want them, everybody's got them.
Right, so they're happy.
So if you don't ask,
Yeah.
that's what you're going to get. And now I think they've come around to the point where they usually give you 3,000 K because they know they'll get complaints otherwise. But don't let them tell you that they can't get the 2700 or the 2200 Kelvin. They are out there, they're very available, and at the same price.
Just curious, in places where the bluer LEDs are already established, can there be any kind of shading that could
Yes.
alter? Okay.
So there are certainly any of the energy companies, if you call them up, even for the street light that's out there now, they are obligated to come out and put a shade around it to control where it goes. So a lot of the LEDs, they're flat on the bottom, they don't have a cowl that comes down, they don't have a shade. They do suffer from more glare because you can see it. A lot of the HPS lights do have shades on them of some sort. So that's one thing, they can put those on there. There are filters that are out there where they can retrofit it and put it over there, and it filters out a lot of the blue. They are not very available because they're kind of expensive to make. So they're hard to get, and they cost a lot of money. So usually the towns don't want to go that way. But for so many that have just bulk converted over to all these really blue LEDs, it's going to have to be an option for them.
And how many years will the terrible blue ones that they put in, will they last 30 years or? Yeah.
Because that's one of the reasons why they were adopted as streetlights, because LEDs last for a while. I don't know what it is with my luck, but I buy a bunch of these for my house, and then like half of them designed obsolescence, right? They make half of them faulty, so you have to buy another one. But if they're working right, the LEDs will last for 30 years. Yeah. A lot of the bylaws we've been writing in sunset clauses that says that when 20% of the lights in a parking lot go, you got to replace them all with the lights that are compliant. So there's lots of different ways to write these bylaws. And in Southborough and in Beckett and most of the other towns, it covers everybody. It covers the lights that you have shining in your backyard, because that goes out into your environment, goes in your neighbor's yard. And you know, a lot of folks push back and say, it's my house, it's my lights, I'm going to do whatever I want with them. Yeah, you don't want to do that. It's really about coming together as a community and making this decision together. We don't want to bring the fireflies back and the stars and everything else.
So this information here would have a lot of what you're sharing tonight?
Yes, and that's the best source you got. That's the International Dark Sky Association. There are a bunch of pamphlets on different things there. Grab them, read them. It's great reading material. Just make sure you're reading it under a nice warm light. I want to see them produce those pamphlets where somehow they change the ink on them so that if you shine your light with too blue, it just wipes it out. The print just disappears like the Marauders map in Harry Potter.
Listen, I've been noticing over the last few years the reflective passive lighting along the roads has gotten really good.
Right.
Is that true? I mean, they seem so bright.
It is.
I'm thinking, well, we don't even really need
No, we
streetlights
don't.
that much.
There are some, very few, but some towns that have sort of invested in those types of lights where it's more passive. Or in solar lights that are relatively dim, but they don't cost anything to run. One of the best implementations of park lighting I've ever seen. I have not actually been there, but there's a couple of different lighting designers that have worked with folks on bylaws where, you know, the safety bollards that they have when you pull up to like the bank drive-in or whatever, a CVS or something, so your car doesn't run into the building. They make those, they're about this high and they're really pretty. And they have a band around them with a cowl on top that shines light. It's below eye level. It shines outward pretty laterally, but because it has a cowl, it doesn't come up. And it's shining exactly where you need to see it, on the ground. Mm-hmm. And it's wonderful because you never go anywhere and you never see lights mounted here. You always see them up here, right? You put them on your house and they're up there. Try putting them at your knees. Because that's where you need the light. You need the light around here to illuminate those things. You don't need it anywhere else. And so the higher we put the lights, a lot of towns have ordinances where they restrict how high you can put a light to try to control that. But we don't need the light up there. It would be really weird if you had your house light like knee height on the outside of your door, but it's probably the best place to put it to illuminate the steps, right, or what you want to see there. So, but those are wonderful implementations because they're lights that can't possibly have glare. They're very warm and they're scattered. And one of the things I didn't get to talk about enough was just the biology of your eyeball, and that you have a tremendous capability when your pupils dilate, when it gets dark, to be able to adapt. And that if you're out just for 30 seconds outside and you're in the absence of glare, it's amazing how a very dim light outside can provide plenty of light as long as you give yourself a chance to adapt. So the conundrum is that we think, well, that's not bright enough because you just walked out of your house and there's bright lights everywhere and it's like, I can't see very well over there, so let's make this light brighter. But the reason you can't see over there is because all the other lights, it's too bright. But if we actually had a lot of dim lights and when you walked out of your house it seemed like it was too dark, a bit too dark, within 30 seconds your eyes would adapt and you could see so much better than with all the bright lights. So it's this juxtaposition of what we think we want and how to get it, and just being out of whack. So we actually want dimmer to see better, and that's kind of tough to convince folks of.
So I live in a village where there seem to be a lot of lights, like they're kind of the amber that you mentioned.
Yeah.
But the glare, I mean the expense. How do you convince, or how do you make the argument? I sometimes go to the selectmen's meetings.
Yep.
How do you make the argument for what is too much? I mean, too much lighting in a small street. That doesn't seem to be a safety issue.
No.
Yeah.
It's very difficult. It's very difficult. Some of the best cases I've seen have been where the select boards have been open and transparent about changing over the lights. They have gotten the energy companies to come out and they take a main street or they take a side street and they change all the lights on that. And then the next street over, they change it to a different kind of light. The next street over, they change it. And they invite everybody over a period of a month to come out and see them. Come out at night and see them and walk down the street. One of the things that we battle with the most, and this is with ourselves, is the moment you change a light that's been outside your house for 15 years or 30 years, people are resistant to change. If it's dimmer, we're like, oh, that's too dark. If it's brighter, it's like, oh, that's too bright. You got to give yourself time to get used to it. But you also have to give your eyes the time to adjust. Because even the high-pressure sodium lamps that are out here now, they're too bright. Especially, they're not necessarily too bright, but most of them aren't shielded, and they have tons of glare. The bulb actually comes down, and you're looking right at the bulb, which is exactly what we don't want. Those are some of the best implementations because you get folks walking. Pepperell did this, and I think Cambridge did that before they converted their lights over. And in every single case that they did that, the folks that spent time and looked at those lights where they implemented over a whole street, in every single case, they picked the lowest wattage and the warmest bulbs, without even having to educate anybody about the health hazards or anything, because we just prefer the right amount of light that's not so blue. But we need a chance to take it in. One of the best things that can be done, and a lot of towns will do this, like surreptitiously, but they'll turn off certain street lights. Some folks just think they burned out, but most of the time, you're like, well, do we really need the street light anyway? What purpose is it serving? Is anybody really taking a walk at 2 o'clock in the morning? And if you are, you can take a flashlight. And even if you don't, you've got Pittsfield that's casting all their light all over Monterey, right? So you'll be able to see, or take a walk by moonlight, right? We can't be afraid of the dark. Time for us to be over there.
That's a perfect segue.
Can I just make one more pitch? When you're getting ready to write to the select board about the lighting situation here, also, as Destin mentioned, a statewide dark sky bill is before the legislature now, and they've tried to pass it for many years, and it just gets,
It's hung up in committee.
It gets hung up in committee. So if you get a chance to write to legislators, I spoke to Smitty Pignatelli a while ago, and he goes, oh yeah, this is getting to be a big deal now. So, it does really help if you mention this to them. And as an example, I don't know if anyone's been by Beartown State Forest recently, but they have a wall park. And this is a wall pad.
Wall pad, yeah.
Yeah, and it's just like way too bright. And I talked to the guy, and yeah, my electrician put it up, and, you know, he's willing to change it, but, you know, if we have a state law, we can
Yeah.
get going on the right
And
track.
talking to your neighbors. I mean, I give talks about this stuff, and I do the astronomy and all that, and I'm still hesitant to ask my neighbors to turn their lights off.
Same.
You never know how they're going to react. But I'll agree with the video. In the cases where I have done that, and I've told them what I'm doing, they're like, of course. One time I contacted my neighbor across the street in Beckett, and I had to contact them by email because they were seasonal and they weren't there, and they said, well, we just left, we're not going to be back for 6 months. But we have a friend, send them over and turn the light out, because I said at the very least, you don't need this light on for 6 months. When you're outside, the bears will find you anyway.
I think I asked someone to turn off one of those big spotlights on a, you know, that was at the end of a shed, and then actually mentioned it to enough people so that they said they were praising the person who did it, and it sort of, you know, it started something going, and so now they're just totally keeping the light off.
You know, it's my ardent wish that if we could organize things in the state or in multiple towns. I mean, I think that folks here, the select board here, contact the select board in Beckett.
Yeah.
You know, so we can paddle together to do these things in regional areas. But if we, once a year, on a clear night, could have a lights out, just to show the town, go outside, look up for 5 minutes, and go back inside. They're not going to go back inside. They're going to come out and go, wow. That's what's been there the whole time. All we've got to do is shut them out once, and it's the best way to demonstrate the stuff. Yeah, so talk to your neighbors, talk to your Congress people, talk to your select board. Go home, reevaluate your lights.